Hi, I'm Matt Samuel. This is my YouTube video about a dual Pieri formula for double Schubert polynomials in different sets of coefficient variables. So I'll briefly introduce double Schubert polynomials. They represent Schubert classes in the torus equivariant cohomology of the complete flag variety of type A, or Schubert classes in the ordinary cohomology of the product of two flag varieties. One reason to call them double. They are polynomials in two infinite sets of variables, which we abbreviate as x and y, but they're xi for a positive integer I, etc. And they form a basis for the polynomial ring zxy as a module over zy. Now, the double Schubert polynomials are indexed by the symmetric group, and they're denoted by su of x and y for u and s infinity. So that is indeed an S. It's just a little bit funny looking. It's in a different font. So a more detailed introduction can be found in my video on the Schubert seminar channel. So S infinity acts on this polynomial ring. It acts only on the x variables, permuting the indices. And if we take the special element Si, S infinity, the adjacent transposition, we can associate a divided difference operator partial Si, which is defined as an element of the skew group ring as 1 over xi minus xi plus 1 times 1 minus Si. So when you apply this to a polynomial, you're taking the polynomial, subtracting what you get when you flip xi and xi plus 1, and dividing by the difference xi minus xi plus 1. And this indeed always yields a polynomial. In particular, on Schubert polynomials, or rather double Schubert polynomials, if the number of inversions of u decreases when you multiply on the right by Si, then the application of the divided difference operator partial Si to Su of x and y gives you Usi of x and y. But if the length increases, then the divided difference operator sends the double Schubert polynomial to 0. So we can multiply the divided difference operators together, and these combine to form composite divided difference operators partial u for u and s infinity. And these relations are similar to the symmetric group, the relations on products of divided difference operators, except that the divided difference operators, at least corresponding to the adjacent transpositions, square to 0. Double Schubert polynomials can be defined in terms of these composite divided difference operators and a top double Schubert polynomial. So first, we pick an integer n and let w0 of n be the longest element of Sn plus 1. Then we define an associated double Schubert polynomial, Sw0 of n, of x and y, as the product, as I plus j goes from 2 to n plus 1, of xi minus yj. Then, for any u and s infinity, to define the double Schubert polynomial Su of x and y, we apply partial u inverse w0 of n to Sw0n of x and y. Now, this may apparently depend on the choice of n, but it in fact does not. So, the correct indexing set of the double Schubert polynomials, by this definition, is still indeed S infinity. So, I mentioned the double Schubert polynomials form a basis of zxy as a module over zy. So therefore, we can multiply two double Schubert polynomials and re-express this in terms of the basis. And the structure constants, the coefficients we get, cu vw of y, are polynomials in y. So there's a positivity result known about these. Cu vw of y is polynomial in the differences yi plus 1 minus yi with non-negative integer coefficients. This is shown by Graham in 2001. Currently, no positive formula is known, and really none is on the horizon, though some partial results are known. Even more partial results are known for CU-VW setting y to 0, but we still do not have a complete positive formula, and we probably won't anytime soon. Now I'm going to introduce the Molev-Sagan problem. So now we're going to introduce z variables, and we're going to consider the product SU of xy times SV of xz, and we can expand this in terms of the basis of double Schubert polynomials in x and y, getting coefficients, which you could call structure constants, CU-VW of yz. Now, I conjecture that these coefficients, CU-VW of yz, are polynomials in the differences yi minus zj with non-negative integer coefficients. I've tested this up to n equals 5. That's pretty easy to test. But I've been running the test for n equals 6, or rather Kellen Myers has been on his machine since January 2023, and it is currently almost the end of October 2023, so it's been taking a while. But all of this wouldn't be necessary if we could find a proof with algebraic geometry, which may be possible. So some special cases of the coefficients. It may be clear, if you remember the definition of CU-VW of y, if we set z equal to y, these are the structure constants for double Schubert polynomials in x and y. If we set y and z to 0, this is the ordinary Littlewood-Richardson coefficient for cohomology of the complete flag variety. An interesting case is if we set z to 0, this is conjectured to have non-negative coefficients by Kirillov, which I have tested up to n equals 6. And the double Schubert polynomials themselves are special cases of the coefficients. If we set u and w to 1, and I've written u instead of v, let's see 1u1 of x and y is equal to su of x and y. So back to the divided difference operators, they satisfy a Leibniz formula, which is also known as a product rule, where if we take two polynomials p and q, partial w applied to pq is the sum over all u and s infinity of partial u applied to p times this new operator partial uw applied to q. So this is the definition of the skew divided difference operator partial uw. So the significance of partial uw is that for any polynomial p and any permutation u and s infinity, we can express the product p su of xy as a sum over all w and s infinity of this skew divided difference operator applied to p, and setting x to y, partial uw of p set x equal to y times sw of x and y. So the skew divided difference operators give you the coefficients in terms of the basis of a product of an arbitrary polynomial with a double Schubert polynomial. So this in particular implies that CU-VW of xy is equal to partial uw applied to sp of xy. This will be important later. So I can't go without mentioning Molev and Sagan's original problem, since I have named the case after them. Molev and Sagan found a Littlewood-Richardson rule for factorial Schur polynomials, which are special cases of double Schubert polynomials indexed by partitions, and their formula was for a product of two factorial Schur polynomials in the same number of x variables, one also having y variables and the other one having z variables instead. And their formula was positive in terms of yi minus zj. Those of you who are familiar with the geometry, this would be the Grassmannian case as opposed to the complete flag variety for Schubert polynomials. So I've made some progress on the Molev-Sagan case for double Schubert polynomials, I found a Pieri formula which generalizes Tilly's Pieri formula for multiplying a Schubert polynomial by an elementary symmetric polynomial. Specifically, EPK of x and z is a double Schubert polynomial known as a factorial elementary symmetric polynomial, similarly to factorial Schur polynomials. In fact, this is a factorial Schur polynomial. And my Pieri formula allows you to multiply any SU of xy for any u in S infinity by EPK of x and z and obtain coefficients that are positive in terms of yi minus zj. So this formula, at the time of the recording of this video, is not yet published. It's still under consideration, but I did present it at the Schubert seminar. The title is a Molev-Sagan type formula for double Schubert polynomials. So you can actually compute all of the coefficients, Cu, V, W of y, z, using the Pieri formula. The way you do this is you can express a double Schubert polynomial SV of x and z as a sum of products of factorial elementary symmetric polynomials in x and various substituted z variables, so they won't just be z1, z2, they will have different indices, and there will also be signs. So given an expansion of the double Schubert polynomial in this form, we can apply the Pieri formula and sum up the results to compute the coefficient. And this is actually pretty fast. I've implemented a program that does this. You can install it if you have Python 3.9 or higher. Pip install Schubmalt. This will give you 3 programs actually, but the one relevant here is Schubmalt_YZ. I'll mention dominant permutations since they'll be central in what comes up next. Dominant permutations are important types of permutations whose double Schubert polynomial is a product of factorial elementary symmetric polynomials. So through identities between coefficients, being able to multiply by double Schubert polynomials defined by dominant permutation opens up many avenues for computing other coefficients. In particular, it allows us to prove the main result, which is a separated descent formula for the Molev-Sagan case in the paper I mentioned previously. So my Pieri formula allows us to compute positively SV of xy times S mu of xz, where mu is dominant. However, the Pieri formula is not directly useful in computing the opposite product, S mu of xy times SV of xz. Now, I say not directly. It is, in fact, the key to computing this product, but not in the same way. It's a bit more complicated. In general, flipping the lower indices on Cu, V, W, Y, Z can give you a completely different coefficient. So they tend to have very little to do with each other. So I give an extreme example on the slide. If U is a non-identity permutation, then C1U1 of YZ, as I mentioned previously, is SU of YZ. But if you flip the lower indices, CU11, YZ is just 0. So these coefficients are not completely unrelated. Clearly, by commutativity, if we set z equal to y, the coefficients become the same. So indirectly, we see here that if we set z equal to y and take SU of yy, that gives you 0. So the central topic of this talk is the dual Pieri formula, which computes C mu VW of YZ, where mu is dominant. In order to set this up, I'll define these polynomials HP of YQ and Z sub A, and that's a product as I goes from 1 to P of YQ minus ZAI, where ai is the ith element of the set of positive integers a in increasing order. So this set must have at least p elements for the degree of the polynomial hp of y, q, and za to be p. So I call this h. This is a special case of the factorial complete symmetric polynomial. That's what the h is for. So here is the dual Pieri formula, although I don't give all the details here. We'll get into that later. So given mu dominant and vw and s infinity, coefficient c mu vw yz is equal to this sum over some permutations v1 through vp for some p of these h polynomials where the z variables have indices in sets q1 through qp, and the degree of the factorial complete symmetric polynomial is the difference in the lengths of vi and vi minus 1 times di inverse, where d1 through dp are fixed permutations. So, although this is complicated, it proves that the result is positive in terms of yi minus cj. So, the dual Pieri formula completes the story of separated descents that are given in the paper I've been bringing up, a Molev-Sagan type formula for double Schubert polynomials. So, the theorem is, suppose u and v and s infinity have separated descents, which we define as there is a p greater than 0, such that the length of usi is greater than the length of u for all I less than p, and the length of vsi is greater than the length of v for all I greater than p. So there are positive formulas in terms of yi minus ej for cuvwyz, which is the main result of the other paper, and cvuw of yz. We flip the lower indices and use the dual Pieri formula to get the opposite product. So now we can multiply any two double Schubert polynomials in different sets of coefficient variables where the permutations have separated descents in any order. So I'll go a bit into the proof of this formula. It involves pulling variables out of the double Schubert polynomial. So Bergeron and Sottile prove that Schubert polynomials have a coproduct into any partition of the variables, the set of indices of the variables, with non-negative integers d, w, u, v being the coefficients of this coproduct. And they were shown to actually be cu prime, v prime, w prime for some u prime, v prime, and w prime corresponding to u, v, and w. We'll get back to that later. So a more specific coproduct was found with a simpler formula for pulling out a single variable, and I generalized this formula directly to double Schubert polynomials. So given w and an index I, there's a set of permutations di of w, which is the one Bergeron and Sottile defined, and a set of indices qi of w prime w, such that we can write the double Schubert polynomial sw of xy as a sum over all w prime in di of w of this h polynomial, whose degree is the difference in length between w prime and w, which makes sense because the polynomial has to remain homogeneous, of xi and y with indices in this q set, and it's a product with sw prime of x omitting I and y, so we're pulling out the variable xi here. So it's very easy to describe what the q set is. It's the set of all wj such that j is greater than I, and w prime j minus 1 is equal to wj. So just going to give an example here. Set I equal to 2, and V equal to 2, 5, 1, 3, 4. So then I didn't give you the formula for finding DI here, but you could look it up in Bergeron and Sotilli's paper. So DI is 2, 1, 3, 1, 2, 4, 1, 2, 3, and the Q sets are defined there, 1, 3, 4, 1, 4, and 1. So we can write this polynomial as a sum of these h's times the double Schubert polynomials with x pulling out x2. So I can prove this formula on the slide pretty easily. First, we're going to let nabla be the divided difference operators on the y variables, which is more convenient in this case. And you'll note that in acting on the y variables, I flipped the sign of the divided difference operators, so it's alternating. So we can write SV of x and y as nabla VW0n applied to SW0n of x and y. And we can easily pull out an h polynomial from SW0n. W0n is a dominant permutation, so this is just the product of h polynomials as well as factorial elementary symmetric polynomials. So the double Schubert polynomial we get when we pull out xi is written there. It's Sn plus 1 minus I down to S1 times W0 of n, with x omitting I and y, and h n plus 1 minus I of xi and y. So we're applying a divided difference to this. So we can use the Leibniz formula to expand this, and we're applying a straight divided difference to the double Schubert polynomial to get SV prime of xi and y for some v prime, and a skew divided difference to the h polynomial, from which we can apply the Pieri formula to get the result. So it requires a bit of algebraic manipulations, but it can be put in the exact same form as Bergeron and Sotilli's formula. It's just the double Schubert polynomial version. So moving on to the proof of the dual Pieri formula, in the 1990s, MacDonald found a formula for the skew divided difference operators in terms of the divided difference operators partial SI and the simple reflections SI. So specifically, if we fix a reduced word for W, the sum is over all reduced subwords for U, partial SI if the index is not in the subword, and SI if it is. This is for the divided difference operator partial UW. So the example I give here, partial S1, S1, S2, S1. So there are two subwords of S1. So we have two terms to this divided difference, to this skew divided difference. So when there are two terms, we're not in good shape. There's usually going to be cancellation and minus signs, which I call elusive demonic cancellation, because somehow it always ends up positive, but there are lots of minus signs. Now, because of the special properties of dominant permutations and minimal length coset representatives, if we pick a certain normal form for a reduced word for W, there is exactly one term in partial mu W. There is exactly one reduced subword for mu in the normal form for W. And this operator is predictable. It alternately applies a divided difference, then pulls out a variable and moves it to the front, with the front index increasing by 1 through each iteration. So I give an example here. S1, S2 is dominant, and the top permutation is in normal form, S2, S3, S1, S2, S3, and we get one term, partial S2, S3, and then the simple reflections S1, S2 times partial S3. So we can successively apply this operator to get the result. First we apply partial S3, which either gives us 0 or S v S3 of x and y. And then we can pull out the variable x3. You'll see why in a moment. Because then we apply s1, s2, and this moves the x3 to x1. So we get an h polynomial in x1 and these y with the q set, and sv prime of x omitting 1 and I. Then we apply another divided difference. This is shifted. It doesn't have s1. It only has s2, s3. And that acts as s1, s2 on the sv prime. So we have applied the entire divided difference. This gives us a positive result, which is either 0 or a polynomial in this form. So we'll recall that the dual Pieri formula has a form in terms of h polynomials, which are expanded in terms of these permutations v and the fixed permutations d1 through dp. And v0 equals v, vp is the identity, and the di are cyclic permutations that come from the divided difference part of partial mu w. So I can express exactly what the vi are. They're elements of d ci star mu w plus 1 of vi minus 1 di inverse, and the q sets are the corresponding q ci star mu plus 1 of vi and vi minus 1 vi inverse. Now here, ci star is the dual code. You may be familiar with the lemma code. This is just the lemma code of the inverse. So the code is what drives this formula, but the code of the inverse of mu. So there are cases where u is not dominant, but this method still works because the skew divided difference operator has the same form. So the first condition is that uj must be less than uj plus 1 for all j such that u inverse of 1 is less than or equal to j is less than w inverse of 1. Now, that condition must hold if we apply phi of m to u and w, where phi of m of u is the permutation obtained from u by deleting the values 1 through m and subtracting m from the remaining values. So if this relation holds between the two permutations u and w, then we say that u dominates w, and the dual Pieri formula applies. So I pick this nomenclature because dominant permutations dominate all permutations. So when something is called a Pieri formula, like Sotilli's Pieri formula, we'd want to say we can multiply by an arbitrary factorial elementary symmetric polynomial, not just one corresponding to a dominant permutation. And we can do that, although it's extremely complicated, and the proof is not exactly a formula I give, but an algorithm for expressing the result positively. So if u, v, and w are in S infinity, and u is k Grassmannian, then there exists vi, wi, and some pi greater than or equal to 0, such that ui is u shifted left to become k minus pi Grassmannian, such that we have this expression of cu, v, w, y, z as a sum over these ui, vi, and wi of a polynomial pi of yz that is positive in terms of yi minus cj, and this smaller coefficient on which we can use induction. So this also works on v, but the formula is different. So this actually gives us, for free, positivity for multiplying a factorial complete symmetric polynomial by an arbitrary double Schubert polynomial. But I wouldn't call it a formula, like I said. It just expresses positivity. So something I later added to the paper is a duality theorem for coproducts of double Schubert polynomials. So we can connect the Molev-Sagan coefficients, just like Bergeron and Sotilli connected the ordinary Littlewood-Richardson coefficients to coproducts of ordinary Schubert polynomials. So let W be a permutation, and let A and B be complementary sets of positive integers. Then for each dominant permutation mu, such that the length of W mu is equal to the length of mu minus the length of W, there are dominant permutations that you can derive from mu sub A and mu sub B, such that SW of xy is the sum of these Molev-Sagan coefficients, Cu mu A, V mu B, W mu of minus y minus z times Su of xa and y times Sv of xb and z. Now notice the z variables come out of nowhere. They're going to completely cancel, but this is still useful even though the cancellation occurs when you sum it out. But here we have a duality between coproduct coefficients and product coefficients in the Molev-Sagan case that is actually stronger even in the ordinary Schubert polynomial case than Bergeron and Sotilli's coproduct formula. So this allows us to do uniform reductions of coefficients to ones with smaller w. So given u, v, and w, we can express them as multiplication of some permutation by a dominant permutation, and then for the top index we pick a smaller dominant permutation, and we have an equality of coefficients due to the previous theorem. So this actually applies surprisingly often. It's in particular useful in testing positivity of the coefficients, since we currently lack a theorem to that effect. Now, when I mentioned I tested n equals 6 for the positivity of Cu VW y0, which took about 66 hours on my laptop. Now, in that case, I was testing less than 11% of the cases, ruling out counterexamples in the other cases. But if I had used the reduction corollary, I could have reduced this to testing less than 2.6% of cases. So we've applied this reduction, Kellen and I, to running the program for testing the positivity of Cu VW yz, but it's still taking months. So that's all for this video. You can tune in, subscribe to my channel for more, and you can see the link in the description to the original Schubert seminar video that started this off.